So let's quickly solve those questions, guys. What do you think is this limit? Well, very quickly, you can see that if the angle theta is small, sine of a small angle is not doing too much to it, and tangent of a small angle is not doing too much with it. So the answer is simply the same as limit. Exactly, limit as theta goes to 0 of 2 theta multiplied by 7 theta divided by 7 theta squared. I hope you understand that. And the answer is, as some of you are noticing, the answer is 2. Because 2 times 7 divided by 7 will give us 2. Now, what about the next question here? This here is x squared plus x minus 2. So we have that it's a limit where x goes to 1 of sine x minus 1 divided by x minus 1 squared. Well, x divided by, by x minus 1 times x plus 2. And so x goes to 1 means that this part will approach 1 and the remaining part will approach 3. So the answer is simply 1/3. Good. Now what about this one? Sine of 3x divided by 5x cubed minus 4. Well, I can clearly factor out an x. So I can think of it as sine of 3x divided by x. And here I have 5x squared minus 4. Now what happens if x is going to 0? What we see is that this quantity here will approach 3. And this quantity here will approach minus 4. So the answer to this problem is that it is minus 3 divided by 4. What about this one? 1 minus tangent x over sine x minus cosine x, where x approaches pi over 4. Let's do it actually on a separate whiteboard. Okay, you see the question, guys? Limit as x goes to pi over 4 of 1 minus tangent x divided by, what was it, by sine minus cosine. What is that? Helene, are you in this class or you just open the window and leave? Respond. Understood. You have 0 over 0, sure, Christian. But you see, the idea here, guys, what you are not doing enough is recognizing what this thing is. Are you ready? I do have to go, so to hurry. So let me solve it for you, guys. What does it look like? So let's take a segue. What does this limit remind you? So I begin saying limit as x goes to pi over 4, and I will write tangent x minus 1. What does it remind you of? What are you thinking? Do you think someone is doing when they write it? In other words, where are they going? What's their destination? Deriving, one person sees it. We're taking the derivative of what function where? What should be the denominator? No, Dragon, not 0. If we divide by 0, we just simply don't get anything, right? We cannot divide by 0. So the denominator has to be x minus pi over 4. When I see that denominator, I right away recognize that I am dealing with the derivative of tangent x, where x is pi over 4. Understood? That's the definition of the derivative of tangent at pi over 4. And so I know that this limit would equal to secant squared pi over 4, which is simply 2. Right? Secant of pi over 4 is root 2. Square it and you get 2. So this limit will equal to 2. Now I see here 1 minus, so I will see something like minus 2 appearing. Right? So here is the strategy. So I will do this. Limit as x goes to pi over 4. I have here 1 minus tangent x divided by, and I put here x minus pi over 4 times, here I have sine x minus cosine x, and here I have x minus pi over 4. Okay, I look at this limit and I instantly see that the answer will be minus 2. because it's 1 minus tangent. It's negative the derivative limit. Before I continue, are you following me, guys? Do you understand what I am doing? It's very simple idea. But do you understand that simple idea? The last part. So here, guys, look at it. How do you find the derivative of any function, right? So for example, if I asked you, that's why one reason you have to write the definition of the derivative very often. If I wrote derivative of the function, let's say cube root of x, right? Where x is equal to, let's say, 8. What would you be seeing? You would be seeing limit. There are several possibilities that you can see. You can see limit where x goes to 8. Do you remember the definition of the derivative? The cube root of x minus the cube root of 8 divided by x minus 8. That's the definition of one definition of the derivative, and then you recognize the function that is being differentiated by simply seeing it here. You see it? It's this function. And where do you recognize the point where you see x goes to 8? And here you see the 8, x minus 8. Yes? That's what's happening here. Look at it. It's 1 minus tangent, but look at it. Tangent of pi over 4 is the same as 1. Do you agree? I just need to know it's tangent of x minus tangent of pi over 4 that gives me 1. That's why I put x minus pi over 4 on the bottom. You see, x goes to pi over 4. Here I see tangent. And here I just realized that 1 will be equal to tangent of pi over 4. Like this, you see, this is what I'm seeing when I see minus 1. I see tangent x minus tangent pi over 4. And here I see x minus pi over 4. And I recognize that someone is differentiating the tangent function. Do you get it now? You understand, guys, that if you do it my way, there are very few problems. If you do it, I'm not sure what way, you are just solving the same problem in a difficult way again and again and again and again. So this is then back to this problem. This is 1 minus tangent x over x minus 4. Because it's 1 minus tangent rather than tangent minus 1, I realize it's negative the derivative. You understand? It's minus 1 multiplied by the derivative of tangent at pi over 4. The derivative of tangent at pi over 4 happens to be secant squared of pi over 4, which is 2, and I put an extra minus, right? And so I actually did not have the derivative. I just placed x minus 4 to make it look like the derivative, and now I'm dealing with the other limit, yes? X minus 4 is in the numerator. So what is this expression? What is this? So then I look and try to understand this part. So let's see here. If I have sine x minus cosine x divided by x minus pi over 4, if I were to have that, this is the same thing as sine of x minus 1 over root 2 over x minus pi over 4. Good. So, and then minus, here I have cosine x minus 1 over root 2 divided by x minus pi over 4. Are you with me? Why did I select 1 over root 2? That's because sine of pi over 4 is 1 over root 2. And cosine is the same thing at pi over 4. You understand? So this, each part here looks like the derivative of sine at pi over 4. So this part is the derivative of sine at pi over 4. And that will be cosine of pi over 4, so it's 1 over root 2. And the other part is similarly, so this part mute your mics, guys, if you are not talking. So this part, cosine of 1 over root 2 over x minus pi over 4, it's the same as minus sine of pi over 4, which is simply minus 1 over root 2. So then what do I have? I have, you see, what is this number? This number is simply 1 over root 2 minus 1 over root 2, so it's 2 over root 2. And so that means that limit as x goes to pi over 4 of sine x minus cosine x over x minus pi over 4. This limit is simply equal to twice 1 over root 2, which is root 2. So this limit is simply root 2. So the entire result is simply, what is this? This is 1 over it. So the entire result, it's minus 2 divided by root 2, and the answer is minus root 2. If you thought it is difficult, then you are not doing enough. Do you even solve questions after class, guys? Do you go and look into it? You see, this is minus root 2. I did it algebraically. You can do it in other ways. Okay. Let me see if you understand the idea. Here, please tell me, what is this limit? Quickly, what is this limit? What is this limit? And what is this limit? So calculate, please, very quickly. So this is 0, this. I actually made a mistake here. What I meant is that this part should be 64, otherwise Yeah, otherwise you're correct, of course. Okay, Kirill. Thank you, Irvin. So this has to be immediate, guys. Okay. I only see a few people. Okay, Christian, great. Khalid, good. Very good. But I don't see enough people. David, okay, so good. Very good. Christian, you remind me of that caterpillar from Alice in Wonderland. Yes. Sumaya, thank you, great. All right, let's solve it. I mean, this is something you're supposed to know right away, guys. So what is this? This is the derivative of root of x. And exactly at x equal to 1664, right? So the answer is 1 over 2 root 64, which is 1 over 16. What is this? This is the derivative of e to the x, where x equals to 2. And the answer is simply e squared. And this is the derivative of e to the x. where x equals to 0, and the answer is simply e to the 0 or 1. Okay, here is another question, guys. Do you recognize this limit? What is that equal to? Okay, one person knows. What about the rest of you? It's a very important limit. One, two, three, four, five, six, 7, 8, 9. Okay, so a few people know it. It's still, I only heard from 1/3 of the class. This is e to the 5. I haven't heard, for instance, from Helene, right? Some people log on and don't actually sit through the class. I noticed that too. Yes, Dragon. So can I explain this one? That is something we did in a prior lecture. So look into the previous topic, derivatives of exponential functions. That's where it's explained. We can talk afterwards in office. So what is the meaning of this limit? Look at this, guys, right? So if in particular, I have this limit where n goes to infinity of 1 plus 1 over n to the power of n is e to the power of 1. It's e, right? Now, when n is going to infinity, what am I seeing here? I am seeing that this perturbation goes to 0. And what am I seeing here? This is simply 1 over the perturbation. So if I label the perturbation as h, this limit is the same as limit where h goes to 0 of 1 plus h. Now, if 1 over n is h, then n is 1 divided by h. Are you with me? You see, if n is h, then if 1 over n is h, then n is 1 over h. And then this limit is equal to e. That's important for this problem. Can you tell me, please, what is the limit as v goes to 0 of 1 plus tangent v to the power of 1 over sine v? Wonderful, wonderful. Now look what happens. Why do I think the answer is E? I can do it in two ways. One way is to realize this, guys, right? Limit as v goes to 0 of tangent v over v. That's simply the derivative of tangent x where x is 0, which is secant squared 0, which is 1. So what does 1 mean? It means that numerator and denominator are the same when v is very small. That is, that tangent is not doing anything to the input when the angle is very small. You barely notice. Good? So the answer is the same as limit where v goes to 0 of 1 plus v 1 over v, which is e to the 1. We can do it also more slowly, but I don't know. You want to do it more slowly or you're comfortable with it? Another way to be sure that this is right is to say limit. Yes, I'm going to explain the other way. They're all similar ways. You understand? You look at it and you have to see the answer. Limit where v goes to 0 of, you ready, guys? Limit as v goes to 0 of 1 plus tangent v. What I want to see here, guys, I want to see here cosine. So, a second. So I see here sine v. And actually what I would like to see on the numerator is cosine of v. Why? Because this is 1 over tangent. I see what I do is I look at this thing over here. If this is h, as v goes to 0, this is a small perturbation. Then this thing is 1 divided by h. You understand? So that's why I want cosine, because it's the reciprocal of cosine over sine is the reciprocal of tangent. And so to compensate, of course, if I multiply it by cosine, I have to also divide by cosine v, right? So what happens now is I'm seeing limit where v goes to 0 of 1 plus tangent v to the power of 1 over tangent v. And the entire thing is raised to the power of 1 over cosine v. Now, as v goes to 0, cosine v will go to 1. So what we're getting here is e to the power of 1, which is e. You see, so that's doing the same thing slowly. It's much kind of quicker to notice if angle v is small, then tangent can be dropped because it's not affecting v. Because tangent of v divided by v approaches 1 as v goes to 0. Just as sine v over v approaches 1. So what it means is that numerator and denominator are very close to each other. They are essentially the same. You understand? So tangent is not really doing anything here. That's the intuition. Let me give you one more question like this. Be careful. I have to be careful because I can easily make a silly mistake here. So let's see. So we have limit as x goes to 3 of the cube root of sine eight x minus, let me actually make it simpler, 1 second. So sine of let's have it like this, a sine of x minus 3 divided by x minus 3 plus 1 minus 1 divided by x minus 3. What is this limit? Apologies, guys. Could you allow me this correction 1 second? So let's have it cosine minus 1 here. I gave you a hard one actually, so I will answer it for you perhaps, right? So Kirill, kind of good. But not right. So it's not minus 1/6, even though you are very close to the right answer. That's why I said actually gave you a very hard question. Not very hard, it's really how do you understand what's happening here? So this looks like the derivative of the cube root at 1. You realize that this expression, as scary as it is, it approaches 0. So this thing goes to 0. So what Kirill sees is that this is like cube root of h plus 1 minus 1 over h. And therefore, he thinks that the answer is the derivative of the cube root of x, where x equals to 1, which is simply 1/3 1 to the power of minus 2/3, and the answer is then would have been 1/3. Okay, that would have been the answer, right? And maybe Kirill is thinking of something else. Now, if you understand what is cosine, right? So cosine of x, this is something I did with my evening students. How do you calculate it? So it is the same as 1. It is the same as 1 minus x squared divided by 2 plus x to the 4 divided by 4 factorial and onwards. So in essence, cosine, that's why I said hard question. I forgot I haven't taught you, we haven't discussed how to do that. So cosine of x minus 1 is very similar, where x is very small, to x squared over 2. So what I see in that limit truly is a limit as h goes to 0 of the cube root of 1 minus, it's a minus here, right? Minus x squared over 2 minus h squared over 2 minus 1 divided by h. And to make the limit look like the derivative, I will multiply the denominator by h over 2 with a minus, and therefore also a numerator must be multiplied by h minus h over 2. So what we get is the derivative here multiplied by 0. So it's 1/3 multiplied by 0, and the answer is 0 to this limit. You understand? The question is that that I forgot we haven't considered in our class. In office hours, we talked about, one person was there. We talked about, we know how to expand e to the x, right? What is e to the x? How would a calculator calculate e to the x? We know how to do that. Yes? And so we can figure out same ideas for sine and cosine. Anyhow, guys, very quickly, could you tell me the last question mark? Or actually, could you do all those 3 question mark questions? This, and this, please. You see? For 3 question mark exercises, please do them as quickly as you can. So first does not exist, you're saying, Kirill? All right, we'll see. Come on, guys. First, second, third, very quickly. Okay, interesting, Irvin. Why not? Look at them. Good, Irvin. Wonderful. Come on, guys. We have to move faster. Only 3 people answered it. What about the rest of you? You understand that when you have a difficult limit, it's very often nothing more than a definition of the derivative in this, guys. So what is question number 1? Well, I can write it as limit x going to infinity of, actually, yes, so limit as x goes to infinity of you're right, Kirill, right? So it's 4x, it's not 1 over 4x, right? So the first guy, x times, so it would be simply what? So tangent is just oscillating. It jumps all the time between minus infinity and plus infinity, and times x, it's growing. So it's like this in this first question. First question here, it's simply like infinity multiplied by plus minus infinity or stuff in between. So it's clearly not an existing limit. It doesn't, it's not defined. You see how I'm doing it? X is just growing larger. As x goes larger, I rotate around the circle. Sometimes it's also sometimes 0. So it's all the values in between. So I have large number multiplied at times by 0, at times by non-zero, or at times by a very negative number, or at times by very positive number. So the first limit does not exist. What about this one? Second limit. It's simply 1 plus 5t to the power of 1 over 25t. So that's the same thing as 1 plus 5t to the power of 1 over 5t. The entire thing raised to the power of 1/5. So that will go to e to the power of 1/5. Good? Next. Well, next is this limit. That's nothing more than the definition of the derivative of tangent at 1, because sine of y and y are going to 0 at the same rate. So it's the definition of derivative of tangent at 1. And what we see is that it's not at 1, sorry, at pi over 4, which is secant squared pi over 4 or 2. Good? What is this, guys? Cosine of z over z minus pi over 2. Could you please calculate this limit? Last one here. That's okay, great. This is the derivative of cosine at pi over 2. You see that, guys? Nothing more than the derivative of cosine at pi over 2. which is minus sine of pi over 2, which is minus 1. I'm glad you see that. So let's move on. Now we are talking about the squeeze theorem, guys. Are you ready? So this is, I'm not sure how, so it's very difficult to apply this theorem, but imagine that yes, guys, here is, thank you for asking. I mentioned to you again, guys, there is never any restriction. You can join any of my lectures. You can go to probability. You just missed already quite a few lectures there, right? But join the evening section if you want. Join the morning section. Oh, join as many times as you like. Go to office hours in the evening if you like. It's very easy. And maybe do that, guys. You can see the difference. Maybe it's because of me, right? In the evening, I'm, I guess, maybe hyper, or maybe because the other students are more excitable. It's hard to say, right? Here I'm falling asleep. So evening section is, yes, it's party. So truly come to the evening section, maybe get excited. Okay, so here, let's talk about the squeeze theorem. So suppose that it's very difficult to figure out the limit as x goes to a of f of x. So it's like a cockroach not wanting to be trapped. You see? So imagine that what you have is you have this cockroach, and the cockroach is running in a very complicated pattern. Yes? And then what you do, you want to trap the cockroach. So you want to trap the cockroach near the point A. So what can you do? You can imagine you have this finger, and the finger traces this curve. So there's a pencil attached to the cockroach, so that's the curve traced by the cockroach. And then you have this finger, and this finger is always keeping the same x coordinate as the cockroach. You understand? So the cockroach moves, the finger follows. You understand? The cockroach can go up and down, but the finger is always keeping the x coordinate. You understand? So it's like this. Look at it. Okay? The x coordinate of this lower curve is kept. And then I have another hand that keeps the same x coordinate as the cockroach, but it's always above the cockroach. So I have this. Okay? You understand? The cockroach is always in between my fingers, and my fingers are closing at this point. Yes? You understand? So, and I know that lower limit and upper limit are converging to the same number L. That will force the cockroach to also converge to the number L. That's the squeeze theorem. Let me give you an example. Okay, here is that idea. So let's say that my cockroach is the function x squared times sine of 1 over x. Okay, and I want to find the limit as x goes to 0. Perhaps it's not a very easy limit because you can see that sine is rotating around the circle, and when x is small, then 1 over x is a very large number. So we just make x a little smaller, and you move by a large number. You understand? So the sign is just jumping wildly between -1 and 1. Okay, but I also multiply it by x squared. So here I can flunk this function by two simpler functions, and I do it as follows. Whatever is sine of 1 over x, it's always between -1 and 1. Sine of anything is always bigger than or equal to -1 and less than or equal to 1. And then if I multiply by x squared, look at it, I have this bound. You see, I have that there is a lower function flunking from below and another function flunking from above, and the limit of each of them, minus x squared and x squared, converge to 0. That forces the middle guy to go to 0 as well. You understand? So here is another exercise. Do you think you can figure out how to do it? So x going to 2, 2 times x minus 2 to the 4th power, sine of 1 over x minus 2, cosine of 1 over x minus 2. Can you find this limit using the squeeze theorem? Okay, two people got it. It's a very silly application of it, but yes, but let's see what we get there. Here is how we're going to do it, guys. Are you ready? So I need to find nice functions. So I can observe that sine of an angle times cosine of an angle, each of them is between -1 and 1. So altogether, this entire thing is oscillating between 1 and -1. Okay. And then I know the limit of the other expression. Yeah, the other expression goes to 0. You understand? I can ignore sine and cosine because they're just numbers between. So this thing goes to 0, and it's like 0 times -1 or 0 times +1. It really doesn't matter. It's gonna go to 0. That's the idea. Here is what we do here. Okay, so yeah, you see, so this expression is between -1 and 1. If I multiply everything by 2, x minus 2 to the fourth, then this part goes to 0 and this part goes to 0, forcing the middle guy to go to 0. You follow the idea? Very simple. It's almost a trivial application of the Squeeze theorem, if you ask me. You see what happens here, guys? It's because this sine and this cosine, what are they contributing? They're just jumping wildly between -1 and 1 and everything in between. But this part is dragging everything to 0. 2 times x minus 2 to the fourth is decreasing the amplitude. Here is another one. Can you do this one, guys? And I gave you a hint. I put something here. You see this expression? Limit as x goes to 1 of this plus 5. Can you figure out what it is? Wonderful. 2 people know it. Okay, 3, 4 people. Exactly. So, okay, guys, so let's go on. Here is what we can do. I can first deal with whatever I called g of x. All of this thing, I can figure out what the limit is about. So you can see that because there is, so you have e to the x times tangent times cosine, all of this will go to 0 necessarily, because there is x minus 1 squared, and that goes to 0. Everything else goes to a finite number. Okay, and cosine is between -1 and 1. You see, so there is basically, if you look from below 5, there is oscillation between -1 and 1, and x minus 1 squared will dampen this oscillation to 0, and what survives is 5. All right, so then one brief mention. I might not go over the full lecture as we are running out of time. So many of you, and probably even after I show it to you, I don't remember it. I wrote it very quickly, so you don't just. I make mistakes in some of my notes. So those were notes from last semester. You probably want to put everything as gx, not just what I underlined. Put the other things as well. You see, you can very easily observe heuristically that all this complicated expression is just dampened to 0, because you have cosine is causing the oscillation. Everything else is dampening it to 0. I probably thought that cosine is the oscillation and g is this thing that I can easily control and show equal to 0. So here, guys, what I want to say. So maybe I will not convince you with this lecture as well, but I want you to understand that the way mathematical questions come about, it's not like find the derivative of something. It is, let's say, here is where I try to explain why stopping a motorcycle by just connecting a chain and doing this directly is not as effective as, let's say, wrapping the chain around the trunk. Why does this improve? You see, notice I'm not, it's not tied around, it's just a loop, right? Why is this way of trying to stop a motorcycle easier than doing it directly? And then I go through calculus ideas. So here is that tree trunk, or this post, and then I break the segments into. I imagine that it's made out of many line segments, and then I examine the physics on each piece, and I come up with a formula that looks like this. You see? And then I recognize that this is the derivative, more or less. And by working it through, I come up eventually with this expression, which means that if you angle the chain around the trunk, it will amplify your force exponentially. You understand? The point of this exercise, you can look at it and we can discuss it afterwards. You can see many of such examples in the physics book that I have on my website. The point is that when you are thinking, when you're using this calculus to any purpose, you are not going to have questions, find derivative of. You are having this very loose question, which you then have to formulate. And the formulation will first appear in the form of the definition of the derivative. And then you can then use the shortcuts. You understand? So you have to be very familiar with what derivatives are and what's the definition. Then I talk about trigonometric limits, guys. So I don't have much time for this. I think I will skip it, but I use the Squeeze Theorem. That's the first non-trivial application of it. I use it to describe trigonometric limits. I prove finally why is it that limit as h goes to 0 of cosine h minus 1 over h is 0. And then I do the same thing for sine. If you are interested to have this discussion at some point, just let's do it in office hours. Okay. So here I explain finally why those trigonometric limits rigorously are what they are supposed to be. Okay, great. So we finished trigonometry, and let me tell you finally we are ready to have an exam. Ooh, let's wake up. When is the exam going to be? I will probably post it within a week. And then when I post it, you will have enough time to do it. Quite a lot of time even, right? So avoid any temptation of writing work that you do not know, don't understand. Because if I decide that you don't know this material somehow, if I think you're suspicious, or I'll do controls, then I will do them in person. I'll ask you to solve a question live when the camera is on. And when I decide to do that, I hope I will not have to. If I decide to do that and you decide not to turn your camera on, or not to come and talk to me, then I'll just simply deduct the points. You understand? So the exam will be very easy because I'll give you tons of time, and therefore also perhaps easy to cheat. Although I'll try to make it, I will try to make the questions so that you cannot just solve them using a computer. You might buy them, which, by the way, the school has a way to figure out who bought the solution. You understand? So if you actually are paying for someone to solve it, and that will be on the website, I might find out. And the easiest way I can find out is, of course, by talking to you. If I realize you know nothing and your exam score is 100 or 90 or whatnot, or you answered questions that they will be trap questions. If you answer those questions, that means you are pretty good in mathematics, right? You understand these concepts well. And if I then see that you do not understand them well, I will assume you're cheating. Do you understand? The exam is going to be on paper. You will send me a scanned copy. I will give you further details later on. Okay, when the exam is ready, I will notify you. Be prepared. No, you can ask me office hours questions. So, and by the way, one other thing is that your final exam will be not administered by me. So it's very dangerous, and it is worth lots of points. So not only you don't know, if you survive my exams and I haven't caught you cheating, you might not survive the final exam, which will be timed. So avoid all temptations to do that. You will have plenty of time. I'm very loose with time. If you say you're not completed in 1 week, you haven't completed in 1 week, I can give you even more time. So relax about the timing. Just focus on understanding the material. Final is your most dangerous point. All right, let's go through chain rule and implicit differentiation. Are you ready, guys? Next topic.